this video we're going to talk about rational exponents, applications of rational exponents, and I was going to title this Advanced Topics for Rational Exponents, but I decided because I'm just doing 3 examples here, but they're lengthy examples and they're all applications, I thought it'd be better to title this Applications. The prerequisite before you can understand any of this, you have to really be very aware of how rational exponents work, including integer exponents and all different the laws of exponents in general, and radical notation and radicals. Alright, so let's take a stab at a first example here. This example is actually from the textbook Modeling Graphs and Functions by Bruce and Kathy Yoshiwara, and I think this is from the 2nd or the 3rd edition of that textbook. The table below shows the exponent p in the allometric equation for some different variables related to mammals. So a variable is equal to some number times the body mass raised to the p power. Now a lot of this seems very kind of like, when students first read this, they get very intimidated. But what you need to be able to do starting in this level of mathematics is to truly not allow your intimidation to scare you out of a problem. Essentially, they're just saying, listen, I got an equation, variable equals k times body mass to the p. Okay, that sounds horrible, doesn't it? But let's see if they give me body mass values or variables or whatever. And you see this table here. This table gives me values for, or well, not values actually, they just give me variables. Like the home range size is the variable. It's equal to some constant times the body mass raised to a certain power. The lung volume for a mammal is equal to some constant times body mass raised to the 1.02 power. The brain mass for a mammal is equal to some constant times the body mass of that mammal raised to the 0.7. The respiration rate, same thing, right, is equal to some number times the body mass raised to the negative 0.626 power. So part A says match each equation to one of the graphs. Now, I'm going to rewrite the equations down below, or at least the exponents down below, so you can see what I'm talking about. So here we have some graphs, and then I've made this table again where our variables home range, lung volume, brain mass, or respiration rate, and then the powers related to those variables are 1.26, 1.02, 0.7, and negative 0.26. This is super important that you're able to interpret from information what the look of a function may be, or some situation like this where they give you a power. You should be able to say something about the function. This marks the difference between a C student and an A student, or a D student and an A student. A students are able to go to say to themselves, okay, listen, if a power is greater than 1, so if I look at like x to the 1.26 power, then every time I increase the value of x, so let's say x becomes 2 or 3 or 4, it's being raised to a positive power, a power larger than 1, so it's going to get bigger. So every time I take a step in the x direction, the output's going to get larger and larger. Whereas something like this, x to the negative 0.26, every time I plug in a different value of x here, so like x equals 1 will lead to an output of 1, because 1 to the negative 0.26 is 1. When I plug in an input of 2, it's going to return 1 over 2 to the positive 0.26 power, because, well, that's what the negative exponent does. It takes the reciprocal. And then you can plug that into a calculator to find out that that's roughly 0.84. And if you plug in the number 3, it'll be even smaller. So this is telling me that if I have an exponent that is negative, as x increases, the outputs get smaller. So let's actually talk about that one first, since I've already started. So we have some variable, the respiration rate, is equal to some number times some base, all of this very unknown, raised to the negative 0.26 power. Now let's just pretend the base is 2. Or yeah, let's pretend the base is 2. So we'll make a table here. and I actually started a table. So I'll say the value of b, and then we'll say approximately the value of v, because it's not really the value of v. But we made a table over here when the base is 1. 1 to the any power is just 1. So v is roughly 1. I mean, it's actually k times 1, but I'm not really worried about k. When b is 2, again, we did this over here, v is roughly 0.84. When b is 3, well, we have 3 raised to the negative 0.26 power, and you can just go ahead and open up your handy dandy graphing calculator, and I'll just take 3 and raise it to the negative 0.26 power, and you see that's 0.75 roughly. Okay. Now again, I want to convince you that actually each of these has a multiple of k in front of it, right? If I put a value for b in here, it's actually k times whatever that number is, really what it is. But the fact is, you see that as the numbers increase, we can go to 10 here, you'll see that 10 raised to the negative 0.26 power will be even smaller, 0.55. So this tells me that this negative exponent causes my outputs to decrease. So this means that as the as we increase the value of b here, that our respiration rate decreases. And in reality, if you remember from the original problem, that thing we were calling b stands for body mass. So we're actually saying that as you increase the body mass, the respiration rate should decrease. Now, which of these graphs show that as we increase x values, the outputs decrease? Now, it's definitely not the first one, because that one's increasing. Second one is also increasing, and third one is also increasing. So this right here, this graph right here, must represent the respiration rate. So I'll put that here, respiration rate. Okay, so that should be all right. Now let's take a look at the other ones. In fact, maybe I'll clear out the rest of this page and just work on the home range next, or maybe I'll just go ahead and compare home range, lung volume, and brain mass all at once. So here we have, I've just rewritten it out here. The home range is just given by the function v is equal to k times b to the 1.26, where b is body mass, v is just their home range. Lung volume is equal to k times the body mass to the 1.02 power, and brain mass is equal to k, some constant, times the body mass to the 0.7 power. And in each of these, I'll just take equivalent values. So I'll try body masses of 1, 2, 3, and 10 for each of these. And what I'll do is I'll plug in everywhere. For each of these, I'll plug in the number 1. Well, it turns out that when you plug the number 1 in, they're all pretty much at 1. So we'll just say that. But we'll then plug in the number 2. So like this first one, I'll raise 2 to the 1.26 power. And the second one, I'll raise 2 to the 1.02 power. And the third one, I'll raise 2 to the 0.7 power, and so on and so forth. So let's go ahead, grab a graphing calculator here, and go to work. And let's see, 2 raised to the 1.26, and then I'll do 3 raised to the same power, so I'll just hit entry and go back here and do 3 to the same power. And then finally, second entry, and I'll do 10 to the same power. Insert here. There we are. So this is what I get for the home range. This might be in miles or something like this. 2.4 if their body mass is 2. If we increase the body mass to 3, the home range increases to 4 miles, let's just say. And if we increase the body mass to 10, whatever that means, the home range will increase to 18.2. That basically means the larger the animal, the more daring they are, the further out they go. Now let's take a look at the next group here, the raised to the point or the 1.02 power. So we have 2 raised to the 1.02 power, and that'll give me 2.0 really when I round to the nearest tenth. And then we'll do the same thing. We'll just regurgitate this one and throw in 3 in the place of 2. That's 3.1 roughly. And then we'll throw in the number 10 here. And I get 10.5. Actually, what's interesting about this one is that as a creature, as a mammal increases in body mass, the lung volume increases about at the same rate. And finally, let's look at the brain mass. So let me clear this out. 2 raised to the 0.7. And then 3 raised to the 0.7. It's just faster for me to type it this way. And then 10 raised to the 0.7. So let's see. A mammal with body mass 2 has a brain mass of 1.6. You increase the body mass again by 1 step, and the brain mass only goes to 2.2. You increase the level 10, and it's only at a brain mass of 5. Now here's the deal. If you look at these tables here, look through them, which one increases the fastest? Well, you can see that the brain mass actually doesn't. In fact, the brain mass is actually the slowest. The one that increases the fastest is the home range. In other words, as an animal gets bigger and bigger, the home range actually increases what a lot of students say is exponentially. It increases really quickly. So which of these remaining 3 graphs increases the fastest? Well, that would be this one. It increases faster and faster. So this must be the home range graph. So that's a graphical view of, remember, this is body mass versus home range. This one over here is body mass versus respiration rate. Now the lung volume, let's take a look at this one. It's almost the same numbers. The same input leads to the same output almost. 1 goes to 1, 2 goes to 2, 3 goes to basically 3, 10 goes to almost 10. So this is sort of like a line. 1 goes to 1, 2 goes to basically 2, 3 goes to basically 3, and so on and so forth. So this would be the third graph. This would be the body mass versus lung volume. So as a body mass increases, the lung volume increases at the same rate. Finally, the brain mass, which is a very sad statement. The larger the creature gets, well, the brain mass does increase, but not as quickly as the body mass is increasing. So it's sort of like, it just kind of deflates after a while. It doesn't deflate, obviously, because you're not losing brain mass, but it's a diminishing scale of return. So as the body mass gets larger and larger, the brain mass doesn't really keep up with it. That's this situation right here. So this is body mass versus brain. That's how you would do a problem like this. Now there's a secondary part to this, but I want to make sure that people really do understand this concept. People get very intimidated when I say, oh my goodness, look at all these variables and stuff like that. The fact is, you're just talking how large a creature is. You get to select, and they tell you what the exponent is. So you could say, well, if the creature has a body mass of 100, then and you want to determine home range size, it's 100 to the 1.26 power. Yes, I know there's a k in front of it, but right now we're just kind of ignoring the k. Now the part B of this, explain how the value of p in the allometric equation determines the shape of the graph. Consider 3 cases. P is greater than 1, p is between 1 and 0, and p is negative. Well, this p being negative, let's start with that one. If you go back to our graph here, the p being negative was, the power being negative, that is, was related to the respiration rate. And that's the only one that's decreasing. So this is a good lesson here. P being negative, or the power being negative, implies a decreasing graph. Now that's for this by the way. That's for this equation. But still, it's good to be able to analyze this. Then we move on. What about p between 0 and 1 versus p being greater than 1? Well, let's look. Let's find the one that's where the power is between 0 and 1. That's the brane mass right here. And if you look at the brane mass being less, or the power on the brane mass being less than 1, it means that it's an increasing function. The graph is increasing, but it increases by less and less every single increase in brane mass. In other words, it's increasing, but it increases ever more slowly. So increasing, but the rate of increase slows down. Now we take a look at our example where we have a power greater than 1, and probably this one I'd like to look at the one where the power is much greater than 1, like 1.26. And you can see it's increasing, and it's increasing ever faster. So every step it increases more quickly. That's not really proper English, but you know what I'm saying, right? So as I write it right here, it's increasing, and the rate of increase is getting faster. It's getting faster and faster and faster. In other words, much larger and larger and larger. So let's try another example here. Again, this is an example from the Yoshiwara text, Modeling Graphs and Functions. The gourd species, so you know what a gourd is. A gourd is like a squash or a zucchini or pumpkin, right? The gourd species Trichosanthes grows according to the formula L equals A D raised to the 2.2 power, where L is its length, D is the width. So essentially we have a relationship between the length and the width of the gourd. The species Lagenaria has the growth law L equals AD to the 0.81. So we have two different species. Okay? Trichosanthes and Lagenaria. I hope I'm saying that correctly. So you can think of one as a pumpkin and one as a squash. Okay? By comparing the exponents, which gourd grows into a long, thin shape, and which is relatively fatter? Now that's a really good question. So let's go ahead and approach that first. And this is intimately tied actually to the last problem. Remember the last problem? We had said, well, when the power is greater than 1, then this output here increases faster and faster. So I'm going to write this. Since 2.2 is much greater than 1, L equals AD to the 2.2 power increases faster and faster. So as we increase the width, the length increases much faster. That's essentially saying, like, let's say you start with a gourd that is like this. Okay, so you have some type of gourd. Gourds are all the shape. I just drew a diameter there. But as I increase that diameter, let's suppose that I increase the diameter to this size, the length will actually increase much faster. So we doubled the diameter, but the length might actually triple or quadruple or something like that. Okay, so we get something like this. And so this lends itself to a very long shape but skinny. Okay, and so that means that the Trichosanthes? The Trichosanthes will be a long, skinny shape. On the other hand, the one that's relatively fatter, obviously we're going to know that that's going to be the other one, but let's just talk about it. Since oops, I misspelled that. Since the power on our second equation for the Lagenaria gourd is less than 1, just from our last example up here, when the power is less than 1, it's right here. Since when the power is less than 1, you can see that in this case the brane mass, we have it that it's increasing, but it increases ever more slowly as time goes on. So in other words, don't think of brane mass and body mass here. Instead, think that we're increasing the diameter of the gourd, and as we increase that diameter of the gourd, the length increases, but just not very quickly. It actually kind of, its increase in length slows down as time goes on. So, since our power is less than 1, the length, which is equal to AD to the 0.81 power, increases, but more and more slowly. So this means that, let's say I had a gourd, and I'll draw it this way. You have a gourd with a diameter like this initially. Okay, so let's just say we have a gourd that looks something like this. If I increase the diameter by, let's say, twice the amount, while the length of the gourd will increase, it'll just not really increase that much. It'll increase, but not a lot. And in fact, over time, it'll just be a much fatter gourd than the other one. So let me write that in here. Now this is just interesting because these are actually species of gourds, and you can actually learn something other than math here. The second part of this first question is which species is called a snake gourd and which is called a bottle gourd. You can kind of guess. This is the bottle gourd, and the one up above, the long skinny one, is called a snake gourd, unless somebody wants to play a cruel joke and misname them. Now the snake gourd reaches a length of 2 meters with a diameter of only 4 centimeters. Find the value of A in its growth law. Now, let's go ahead, and I'm going to erase all this stuff here, and let's go ahead and talk about how to find the A in the growth law for the snake gourd. Okay, and we've already determined the snake gourd is the equation for it is L equals AD to the 2.2. It's the one that has the higher power. Well, they give us a couple pieces of information. When they give you 2 pieces of information, that essentially gives you 2 of the variables here, which means you only have 1 unknown that you can solve for. One thing I want to impress upon you, they tell me the diameter is 4 centimeters. So let's let D equal 4, and they tell me the length is 2 meters or 200 centimeters. Well, let's talk apples and apples, not apples and oranges. So I want to write this in centimeters. If the diameter is in centimeters, I want to write the length in centimeters. It just would make sense to keep the same units. So here we go. Let's enter this in. L is 200 times A equals A times D is 4 to the 2.2 power. And you see in this equation now, I only have 1 unknown, that's A. So A is equal to 200 divided by 4 to the 2.2 power. And now you can grab a calculator and just punch these numbers in really quickly. So I have a calculator in front of me right here, so I'll just do it. And I get 9.5 roughly. Okay, so A is roughly 9.5. And let's see if we answered. Yeah, we did answer the question. A is roughly 9.5. The bottle gourd, here's the second part of the question. Here they're going to have us find out the growth factor or the growth law, the value of A in the growth law for the bottle gourd. So we'll do the same thing here. The bottle gourd has the overriding equation L equals AD to the 0.81 power. And they tell me that it's 10 centimeters long and has a diameter of 7 in its maturity. So here we are. Now I can easily solve for A by dividing both sides by 7 to the 0.81 power. So A will be 10 divided by 7 to the 0.81 power, which is roughly equal to, when I grab my calculator here, 10 divided by 7 to the 0.81, I get 2.1 roughly. So the A here is roughly 2.1. Some people might wonder, what does that A really mean? It's just like a constant of variation, essentially. Let's see. The giant bottle gourd grows to a length of 23 centimeters. Oh, the giant bottle gourd. Okay, so we have a different kind of gourd here, but we're going to assume that Actually, we're not going to assume. The giant bottle gourd grows to a length of 23 centimeters with a diameter of 20 centimeters. Does it grow according to the same law as the standard bottle gourds? Now, the standard bottle gourd grows according to this law, where A, we just found out, is roughly 2.1. So let's see if the giant bottle gourd follows the same equation, same growth equation. So remember, L is equal to now 2.1 d to the 0.81 power. And they're asking us, well, if the length is 23, will it be true that the diameter should be 20? Well, let's find out. Let's find out what 2.1 times 20 to the 0.81 power is. And this one I might actually bring up the calculator in front of you, because it might just be more beneficial to see it. So 2.1 times 20 raised to the 0.81 power. That's 23.7. And remember, I kind of roughly, 2.1 is a very rough approximation of that. So it sort of is accurate, sort of. So I can believe it. Math is perfect, but the real world is not. So I'm going to say that on this one, yeah, I think it could. All right, yes, possibly. There's a little error in our thing. We got this to be 23 point something, but I rounded that number, so that's probably why. In fact, here's the actual A that we should have used. Let me go ahead and take that A and multiply it by 20. I'm just curious if it will work out perfectly. Raised to the 0.81 power. That's a little bit better. Yeah, I think that's right. I say that's pretty good. All right, good. Okay, so this is the advanced applications, in my opinion, that could be used with rational exponents. Notice they are very theoretical here. These are called concept mastery questions, where you spend more time thinking than you do computing. But that's how things should be done. You should be thinking your way through a subject. You are a scholar, an academic, and this is Socratic. We are going to spend our time being mathematicians and the elite, if you will.